All right, welcome to day 19 of assembly language class. Today's going to be a good day. We're going to start with a new architecture, one we've talked about several times during the semester, but today we're going to cover as much ARM as we can. Before we get started, are there any questions? I'll remind you, you have an exam next week. We still have one more class meeting before the exam. So the exam has a window that goes from Wednesday, start of the day, 8 a.m. on Wednesday till 5 p.m. on Thursday. Same kind of schedule as the first exam we took. So you can still ask questions on Monday, but thinking ahead to that, any questions before we get started? All right, so let's talk about ARM. ARM stands for Advanced RISC Machine. It's a design for a collection of microprocessors designed by ARM Holdings. An interesting thing is they don't actually manufacture chips. They produce designs. They produce designs for ARM, and then other companies can license their chip and manufacture it. This is, you're going to find a lot of contrasts between this and CISC processors like the 8086 we've been talking about, and all of the later generations of that or from that same processor. Trying to follow a RISC architecture or a RISC design philosophy. There are a lot of advantages to ARM listed here at the bottom of the slide. Less complexity, so fewer transistors to implement it, so less power consumed. So this is a really good architecture. It has been a really good architecture for embedded devices. The claim is 95% of cell phones use an ARM instruction set. And a lot of other devices with embedded microprocessors. It looks like Apple is switching over to ARM. I did some reading this morning to verify that. And I hadn't thought of it before and I hadn't considered it, but it looks like their M1 processor that they're using in some of their systems is ARM based. I had always assumed it was Intel, like the other systems they've made. So ARM, it's not a new architecture. It has gone through many revisions. It's been around for a while. It continues to be, or like new versions of it continue to be developed, but it's still continuing to get a lot of attention and be used in more and more systems. What can I tell you about ARM? It is a load and store architecture. So whereas with the 8086, you see a lot of instructions that do operations on memory, you can add something to a value that's in memory. In ARM, you're going to be bringing things into a CPU register, doing operations on it while it's in a register, and then eventually writing it back out to memory. Like typical RISC architectures, all ARM instructions are the same size in memory. We saw 8086 instructions varied in size depending upon what kind of operands they have. But an important part of how ARM or how RISC in general is designed to be fast is all instructions are the same size. So it's easy to go decode the next or go fetch and decode the next instruction because you know where it's going to be in memory. The instructions tend to be simpler than they are in a CISC instruction set. So most of them can be implemented so they execute one instruction per cycle. That's in a pipelined implementation. And we'll talk a little bit more later about what we mean with a pipelined implementation. I think a RISC architecture is a really easy way to try to understand what pipelining is. So we'll spend a little bit of time talking about that. ARM has lots, like any RISC architecture, it has a lot of clever tricks in the design of the instruction set. And we've listed two of them here on this slide. One of them is not just branch instructions, but lots of instructions can be conditionally executed. they can behave, they can execute or not based on the condition codes. And we'll see some examples of that. And on the other side, you get to choose for a lot of instructions whether or not they modify the condition codes. So it's like instructions have little parameters in their behavior, and there are different versions of the instruction or different ways you can set that parameter to make them do either of these two things, either conditionally execute or decide whether they're going to set the condition codes or not. That last part is what I said a moment ago. Many versions of ARM have been developed. And just like with Intel processors, as we've moved from 32-bit architectures to 64-bit architectures, ARM has kept pace with that kind of thing. We'll be looking at the 32 or a 32-bit version of this today, and on the programming assignment where you get to do some ARM. That's what we're going to be focused on. Since we'll be looking at a 32-bit architecture, that means it's made for a 4 GB address space. We already talked about that with 8086. If you're using registers for addresses and you've got 32-bit registers, then that means you can access 4 GB of memory, 4 billion, roughly 4 billion bytes of memory. Everything or a lot of things are kind of scaled up compared to what we saw with the 8086. So before we used byte-sized and what we called word-sized operands. ARM has, at least the one we're looking at, has 3 sizes for operands, byte and word, but here word is 32 bits, so it's twice as big. It's a 4-byte quantity. And in the middle, we've got half word. So a 16-bit quantity would be called a half word, same size as what we would have called a word on 8086. We'll just call it a half word because word is going to refer to a quantity, a 4-byte quantity instead of just a 2-byte quantity. In terms of registers, we said this at our last meeting kind of as an aside. There are 16 registers, each one of them 32 bits in size. And you can use them all, but the first 13 of them registers 0, and that's what their names are like, R0, R12. So instead of having names that, for most of them, instead of having names that reflect what you might do with them, they just have numeric names, because especially for those first 13, you can kind of do what you want with them. But the last 3 registers, 13 through 15, are special purpose registers. 15 is the program counter, so that we might have called that the instruction pointer sometimes when we were talking about Intel. That's the memory location of the next instruction. Register 13 is the stack pointer, so kind of analogous to the stack pointer we had in Intel. And register 14 is the link register, kind of analogous to the base pointer we had in Intel. I'll go ahead and say there's no segmentation, so we don't have to worry about segment registers at all. We've got 32-bit registers, and that's enough to let us access 4 GB of memory. We don't have to do anything fancy about keeping up with the start of different regions of that memory. So some people would call this a flat 4 GB address space. Questions before I move on? What else can I tell you about ARM? It's got condition codes, and they're largely the same as what we had in Intel. Fortunately, you see this in a lot of microprocessors. They've got different names, but there's a N condition code that reflects if a result is negative or not. And we're going to store values, at least for signed values. We're going to store them in sign magnitude, just like we learned about early in the semester. So negative means it's got a high order bit of 1. If it has a high order bit of 0, that means it's 0 or positive. So just like Intel, there's a 0 flag called Z. And it's just like Intel. If it's set, that means the result is 0. If it's clear, that means the result is not 0. There's an overflow flag, and it's analogous to the overflow flag in Intel. It's written as V, but if you just did a math operation and you got a signed overflow, the V bit will be set, otherwise it'll be clear. And there's a carry bit, which is kind of like the carry flag from Intel, but not exactly the same. And we'll take a little side trip to talk about how it's different. You remember, so there was one interesting thing about the carry flag on Intel. And we noticed this when we did subtraction in binary. There were really two ways we could do it. And here's an example just to remind you. So this, as a math problem, this says 1 minus 2, just written in binary. And whether you think of those as unsigned or signed quantities, this is still 1 minus 2. If you had to do this just with binary subtraction, you remember how to do this. 1 minus 0, the low order bit is easy, that's 1. But then to do the next bit, we have to do a borrow. And one way you could think about doing this is we could kind of assume there was, I mean, in this number, there's really nothing to borrow from. But if we want to be able to do this math problem, we could pretend that there's a high order 1 there just so that we can borrow something. It's kind of like we're borrowing from an imaginary bit over on the left. And the original way we did this borrow is we said, well, we can express this in 1s and 0s as saying, well, that 1, if we borrow from that, that's equivalent to all 1s in these high order 0s and 1 extra 1, since this stuff adds up to 1 in the next bit. And then with that borrow, we can do the rest of the subtraction problem. The 2 up there minus the 1 gives us 1. And then these 2 remaining ones, each of them minus 0, gives us a 1. So that's the result. If you thought of this as a signed value, well, the overflow flag reflects signed overflow. That's what we call V in ARM. And we didn't get a signed overflow because just reading them as numbers, 1 minus 2 gives us -1. And sure enough, that's what we got. So the overflow flag would be 0 after this. Normally for the carry flag, at least for Intel, we think of this as, did you borrow out of the high order digit? And here we had to do this math. So we would end up with a carry flag of 1. And that's obvious if you and we're kind of rewinding a few weeks here, maybe a month and a few weeks. That's obvious if you do this with subtraction, binary subtraction. But remember, you could also do this with addition of a -2. And we'd like to get the same result. Remember, if we do this with an addition of a -2, and the processor ought to be able to do this either way. For Intel, at least when we were talking about Intel, when we do the operation this way, we notice that we don't actually get a carry out of the high order bit here. If you if you add, these 3 1s add up to 1 with the carry into the next bit, and each of these doesn't need a carry. So we get a carry bit of 0 here. On Intel, we decided, or at least we explained this by saying, well, Intel can implement this operation either way. They just, if it's implemented this way, they're smart enough to flip the carry bit so that it gives you the right value. It reflects whether or not you would have had to do a borrow out of the higher order bit. That's not how ARM does this. For ARM, they just take the carry bit that you would get from doing the addition, from doing subtraction by adding the negated result, which means the carry bit's going to be flipped compared to Intel. Not every time though, only when you're doing subtraction. So let me back up a couple of slides so I can point to what I'm talking about. So the point here was we noticed when we do subtraction, if we just do bitwise subtraction, we get a carry bit that has what we expect. When we do it by adding the negative, well, the carry bit doesn't give us what we want, but Intel is designed to flip the carry bit if subtraction is implemented like that, and that would be internal to the processor. For ARM, you're going to get the carry bit like you had done the subtraction like this, not flipped. So if you do a subtraction, the carry bit is going to be 0 if there was a borrow, and it's going to be 1 if there wasn't a borrow. Or another way you can think of it is, if I had to put a 1 here to do the subtraction, then the carry flag, sorry, let me try saying that again. If you do the subtraction and you put a 1 here, the result is going to show what the value of that bit was after the subtraction occurred. So in this subtraction, this 1 gets taken down to a 0 because we had to borrow from it. So the carry bit is going to be 0. Otherwise, if I had never actually had to borrow from this, it would still be a 1. So the carry bit would be a 1. Or if you prefer to think of it this way, it's what you get by adding the negative. It just doesn't flip the carry bit. So when you're doing an add on Intel, the carry flag always reflects whether or not you got a unsigned overflow. If you had to carry out of the high order bit, or you had to borrow into the high order bit on a subtraction, the carry flag is going to be 1. But on ARM, it's going to depend on the operation. If you do an add, the add is going to be just like Intel. If you do an add and you have a carry out of the high order bit, then carry is going to be 1. But if you do a subtract and you had a borrow into the high order bit, carry is going to be 0 in that case. So it's just like, or it's like the Intel, like we had with Intel, it's just the bit is not flipped. Questions about that? I'm sorry, that's a little inconsistent. There are other things that will be inconsistent. This is maybe the one that's a little hard to keep up with. Yeah, so a question?
Yeah, what was the motivation behind this design choice? Like, or was it just like, I don't imagine it would be super difficult to
flip like
that bit? Yeah.
I don't have a good answer for that. There's nothing wrong with doing it this way. It seems backward to us because we learned it first the other way. I guess if it was my preference, thinking of the carry as a carry out versus a borrow into, that's more natural to me. So the way ARM does it does seem a little bit weird. But knowing this, you can code to it. I don't know if there's necessarily a performance advantage here. It's not really like flipping that bit was computationally hard.
Well, I think that the big concern would be like if you wanted to check if you had had an overflow there, like because like this, if you're doing an if you're using it as an unsigned value and you subtract 2 from 1, you're going to get, well, whatever the max value of that register is. And if it's done this way, then, or I guess that you would, so if you're checking for overflow after an addition, you would check if it's a,
yes.
So yeah, that's
yeah. So you can still do that. You can still detect overflow. It's just the operation you use to say, did overflow happen, is going to be different if you just did an add versus if you just did a subtract.
Okay.
So I've tried to define the 4 condition codes, or the flags in the condition codes, and fortunately they are mostly the same as what we had in Intel. We just spent extra time on this one that was different. How do these get used? Well, here are the different tests, and we'll talk more about how you do these in a moment, but here are the tests that use the condition codes, and here are their names over here. At least here's the shorthand notation for them. I mention this because this is going to show up in things like branch instructions. So PL, and later we'll see branch on plus. would be if the negative flag is 0. Minus would be if the negative flag is 1, exactly like you'd expect. Same things for signed overflow. There's and you can read this as VC, if overflow clear, if overflow set. I think these all make sense. For comparisons, we're going to see a comparison operation that's the same idea as Intel. It subtracts the source from the destination, but just sets condition codes. And these can be used to compare dest and source. If you subtract source from dest and dest is bigger than or equal to source, then the result better be positive unless you got overflow. And that's just like Intel, that's exactly what this says. If the result is positive and there was no overflow, then dest was bigger than source. Or if you got overflow, then the result's going to be negative. So as long as those match, then dest was bigger than source. The other one down at the bottom for asking the opposite was dest. Sorry, I said bigger than source. I should have said bigger than or equal to source. Because this one, is it the other way around? Is dest less than source? It's just the negation of that condition. Are those two flags different? In fact, greater than is just the same as greater than or equal. It just says, and the result is non-zero, so they're not equal. So greater than is the same as greater than or equal, except it excludes the 0 condition. And less than or equal is just the negation of that. So it's the opposite of greater than. So I tried to explain all of these conditions. I know I'm trying to do it quickly. You can also check condition codes after you just did a plain old arithmetic operation. And if you did, you can think of it as telling you about the result. If the result is positive, then the negative flag will be false. If the result is negative, then the negative flag will be true. Sorry, I feel stupid saying that. And then the same for all of these conditions. If the result is bigger than or equal to 0, then the negative flag will equal the overflow flag. I won't read through all of these, but this is if you want to check condition codes, not after an explicit comparison, but after an arbitrary mathematical operation. Yeah.
In Intel, there were different comparison operations for when you're using signed or unsigned values. Is that the case here?
I got another slide for that. So that's a good question. And we have the same thing here. So the ones on this slide, these were all, these all made sense for signed values. And here are the equivalent ones for, or at least here are kind of analogous ones for unsigned. And this is some of what we just talked about. If you just did a comparison, well, then at least you just did a subtraction, because the way to use these flags depends on whether you did an add or a subtract, but a comparison is a subtract. So if you just computed dest minus source, if dest is bigger than or equal to source, then carry should still be 1. At least if you think of carry as an imaginary digit off to the left that you may or may not borrow from. And as long as dest is bigger than or equal to source, then you don't have to borrow from it, and carry will still be 1. If it's the other way around, then carry will be 0. So those comparisons really show up as carry set or carry clear. That's why they have those names, these names over here, as opposed to higher than or equal, or lower than. And I'm using those terms higher than and lower than because that's the ARM terminology here. Remember, on Intel, we used above and below, but for unsigned comparisons, they use high and low in at least how they made up these names. So if the dest is strictly greater than source, that's the same as greater than source, except excluding the 0 condition. Sorry, I've got slides for these. And the other one is just the negation of that. So as long as you, really for me, as long as you can figure out one of these, the rest of them kind of follow naturally. Just like with signed results, you can use these to look at something that, to look at a result that you just computed other than, if you just didn't add or subtract. But like we saw before, the way to use the carry bit depends on whether you just added or whether you just subtracted. So if you just subtracted and carry is 0, that means you got an overflow. If you just added and carry is 1, that means you got an overflow. The last ones, the ones at the bottom, are easy because they only depend on the 0 flag. Whether you're signed or unsigned. If you just did a comparison and the two values were equal, then the 0 flag would be true. Otherwise, it would be false. So the name for that is EQ or not equal. And there's even a condition for always, AL. And that's just always true. It doesn't depend on the condition codes at all. Questions? All right, so we've talked about the registers available in ARM. We've talked about the condition codes, and we've talked about these names that reflect how you use the condition codes. So let's see some ARM instructions. We mentioned that it's a load and store architecture, which means we access memory and then we compute on things that are in registers, and then eventually we write registers back out to memory. So those are the load and store instructions. We'll see examples of ones that, well, first let's just look at some, without stalling, let's look at some load instructions. So the load instructions look like LDR. You can read that as load register. They're always going to load something into a destination register. So that'll be something like R0 or R1. That's what we're writing as RD here. And each of these lines shows a version of this instruction. So the top one, you can get the address of a variable, and that would be something, it'd be what we would have called the data section. In Intel, that puts the address of a variable in the register of your choice. You can put a constant value in a register in that second form. You can go get what's in memory at a particular address. So this goes and gets what's in memory at the address given in Rn with square brackets around it, and it puts the contents of that memory into Rd. So these are your indirect addressing modes. The next one adds the two registers and then gets what's in memory there. The next one adds a constant to a register. And this last one is kind of like the first one, or kind of like this one up here. It gets what's in memory at this particular location, copies it to the register, and then moves the register ahead by this offset, by this immediate value. So it's kind of like a post increment. Notice that there's no instruction like this top one to go get the contents of a variable and put it in a register. And we'll see in a little bit why you can't really do that. ARM can't really encode an instruction like that, but you can do it in two steps. So if you get the address of a variable and put that in a register, and then you go get the contents of memory at that register and copy it into some other register, you've done, well, here we're copying it into the same register, which is okay. Then you've achieved the same thing. Yeah, and I already said that last mode is kind of like post increment. Questions? So you can see we've got a lot of stuff like we had in Intel. I guess if we're missing an addressing mode, it's that one where you add two registers plus a constant. Looks like ARM can't do all of that at once. It's got add two registers, a register and a constant, but not two registers and a constant. For store, we've got fewer of these, but you can't really store an immediate value. So some of those wouldn't have made sense as store instructions. These copy what's out of registers or what's in a register to memory. And they look like the same four immediate modes we just looked at. copy to a location given by a register, or the sum of two registers, or a register plus an offset, or what's in the address given by a register and then bump ahead by some offset. So another kind of post increment or decrement mode. Notice that the operands are backward here, at least compared to Intel, and kind of compared to the loads. Loads, you can think of it as going from the second operand to the first one, whereas here the destination is the second one. So go from this register to this memory location. So the loads and stores pick what goes in to registers. The way I've shown them here, they all work on word-sized data, but they all take little suffixes that let you specify shorter amounts of data. So the forms we just looked at, copy 4 bytes, 32 bits from memory, or in the store instructions, they write out 32 bits. But if you say LDRH, you're asking to load a half word. And in Intel, we kind of had names for the 2 byte-sized sides of some registers. In ARM, you're going to use the whole register. You're just going to initialize it with a half word in the case of this instruction. So this goes and gets 2 bytes, a 2 byte, a 16-bit quantity out of memory, copies it into the register of your choice, and 0 fills the high order bits. This one goes and gets a byte, puts it into the low order bits, and 0 fills the rest. So the point here is you're using the whole register, you're just initializing it with something taken out of a byte of memory or a half word of memory, 2 bytes of memory. These versions are for doing this with unsigned values because they 0 extend the value. If you wanted to sign extend it, if say it was a signed value, that's what these two are for. LDSH goes and gets a half word, but instead of 0 filling the high order bits, it sign extends. Same thing with byte sized. On the store side, you can also save the low order 16 bits of a register or the low order 8 bits. Here, we don't need to worry about sign extension because we're going the other way. It just copies the low order 8 bits or low order 16 bits. So this is all it takes to access memory in different size chunks. It's the same 3 we just talked about, byte-sized, half-word sized, or word-sized. Questions? Once you get something in a register, you can compute with it and move it around. There's a move instruction, but it's not for going between memory. It's just for moving stuff between registers. So move takes a pair of registers and it really copies from the source register to the destination register. If you want to do math, there are add and subtract instructions. And there are 2 versions of each. Since these only work on registers, we don't have to worry about as many addressing modes because your operands have already been copied into registers. That first version takes 3 operands, it adds the second 2, and instead of modifying either of them, it copies the result to the first register. And I wrote down here shorthand for how to read this. So it takes RN, adds it to RM, and then stores the result in RD. There's also a version of this that takes an immediate operand. So if you just want to add a number to what's in a register, you can do that. And you can take this as saying the destination can be a different register than the sources, but it doesn't have to be. Generally, if you wanted to add 2 registers and then store the result in one of those 2, you can override it. That's okay. We could do the same thing in Intel. Down at the bottom, we've got the same operations for doing subtraction. Same, I don't know if there's anything new to say about that. Oh, but we mentioned this before. This is just our first time seeing it. We said a lot of instructions can optionally set the condition codes. And load and store instructions don't do that, but this one can. If you put an S at the end, that tells it to set the condition codes. If you leave off that S, then the condition codes are not modified by this instruction. So this can let you, it makes it easier to do an operation, get the condition codes the way you need, and then do some more operations before you're done looking at the condition codes. So you get to decide whether or not, say, a math operation overwrites what's in the condition codes. Another way to think about this, and we'll see more of this, we kind of saw it on these slides. It's kind of like you're composing an instruction by starting out with an opcode and then sticking little suffixes on it that say details about what you want to do. For the load and store instructions, that suffix says something about how much data you want to load and what its type is. And here, part of this says whether or not you want to modify the condition codes. Same thing here. So this is just pointing out that S at the end says to set the condition codes. Questions? All right. Multiply and divide. We'll try to cover this quickly. I don't know if you'll actually need to use, I don't think you'll need to use this instruction, but maybe it's nice to see. For multiply and divide, just like Intel, these come in signed, there are two different versions. There's a signed and an unsigned version, and you can guess which is which based on their names. So UMUL for unsigned multiply, SMUL for signed. These take 4 operands because they always do a 32 times 32-bit multiply, and that gives us a 64-bit result. So the result has to go in an operand or in a register pair, and you get to pick which pair. So the first register is the high order bits of the result, and that's what it gets. The second one is the low order bits of the result, and then the 2 remaining ones are what get multiplied together. So both the signed and the unsigned have that. There's a signed and an unsigned divide, but those just give you a 32-bit result. They just need 3 operands, and they do 32 bits divided by 32 bits with a 32-bit result. Potentially overflowing, but we already had that with Intel. There was the potential for overflow, even though we were dividing, I think, sometimes a 32-bit quantity by a 16-bit quantity there. On the multiplies, there are some restrictions on the registers you can use. Those are listed in the course readings, but restrictions that generally might make sense, like RDHI and RDLO can't be the same register. You can't store the high order and the low order bits in the same register. There's no good reason to do that. And divide, depending upon your hardware, divide may not actually be implemented in hardware. Not all divide is used seldom enough in actually executing code that they may expect you to just do that in software, and that simplifies the design of the chip a lot, reducing power consumption. So if you're working on a real ARM processor, whether or not you have this instruction might depend on your processor. Questions?
Is there a percent operation or like a modulo?
I didn't see one. I don't feel like I'm necessarily looking at all of the operations, but if you wanted to do that, you might have to do it yourself. So you could do a divide, and then you could use that to compute the modulo. And I'm going to say, since divide itself may not be implemented in hardware, the idea that you have to do some extra work to get the mod if you want that, that doesn't surprise me. I don't know that it's not there. I didn't see it. Other questions that I may or may not be able to answer. All right, what else do we need? It'd be nice to have a compare instruction, and we've got it. It really comes in 2 forms. You can compare 2 registers, or you can compare a register with an immediate value. This is analogous to what we had in Intel. It subtracts the, the source from the destination and sets the condition codes accordingly. And this one, you don't need an S at the end to tell it to set the condition codes. It always sets the condition codes. Otherwise, there's no point doing the instruction. So it doesn't come in optional condition code form. Once you've set the condition codes, what can you do? Well, there's a whole pile of conditional branch instructions, and they all start with a B. You can read that as a branch. So this is a conditional jump in the code. And then remember when I was talking about the comparisons, I mentioned things like, oh, EQ is the name of the equality comparison, or NE for the not equal. It's because those two characters are used in all of the branch instructions. So BEQ branches if you just did a comparison that was equal, effectively if the Z flag is set. BNE is the opposite, and this is just a sampling of them, but they all use names from that previous chart. So branch if carry set, and they all take as an operand a label, just like Intel, where do you want to jump to? So branch if carry set is branch if carry is 1. And then if you want to think of that as an overflow, that's the one that depends on whether you just did a subtract or an add. If you just did an add, branch if carry set. Oh yeah, add carry set would indicate overflow. If you just did a subtract, it would indicate no overflow. Or if you thought of it as a greater than, less than comparison, it would be if the destination was bigger than or equal to the source. And I won't read through the rest of these, but I'm just showing. You've got branches for all of the condition comparisons, including always branching. We said there was an always condition, and there's a branch to always take a jump. We got enough to write some code. So let's write a little fragment of code to compute the absolute value of what's in register 4. I know when you've been working on Intel, it's easy to feel like registers are scarce. You have to worry a lot about what you're keeping in registers. And they're not overly abundant here, but it's nice to have 13 good general purpose registers to keep what we want. So let's assume there's a value in register 4. Let's assume it's a signed value, and we just want to compute its absolute value. So if it's negative, we want the positive version of that number. We'll pretend that we're going to use register 0 to help with this. So we'll assume it has a value of 0 in it, and that could mean we just need to put a 0 in it before we get started. Remember, there's a version of load register, LDR, that lets you put an immediate value into a register. So we could do that at the start if we want to use it to help with this implementation. So if we want to see if we want to compute the absolute value of what's in register 4, first, let's see if it's positive or negative. So we'll compare it to 0. And if the result is positive, then that would mean it must be bigger than 0, or that would mean it would be no less than 0. So we'll negate it, but only if it's negative. So if it's positive, we don't need to do anything with it. If it's negative, we need to negate it. And one way we could do that is we could subtract it from 0. And that's really what the R0 equals. That's what this assumption is for up here at the start. So we've got a 0 to subtract it from. So we'll take R0, subtract R4. If it was, and we'll only do that if it was negative. So if it's negative, that should give us the positive version of this, and we'll put it right back in R4. And that works. That's a 3-instruction solution to negate what's in R4 if we need to make it positive if we need to. Questions?
How does immediate value formatting work here? Like, are you able to input like hex or octal or decimal, however you want, and just mark it in different ways? Because I noticed the little pound sign in front of the zero. How do immediate values work in this?
I'm trying to remember. I'm trying to remember if that was in the slides. Back here when we started talking about load, did we have an, yeah, here we had an equals in front of the const, but I think it's a pound sign. So I don't know if this is wrong or if there's some reason for marking it as an equal here. You put a pound sign in front. I think you can use suffixes like we did before to indicate what type you want. Later in the slides, we've got essentially declaring data like we do in 8086. And there we'll see a bunch of syntax for specifying different values. That's not a complete answer to your question, but we'll see some of that syntax. Other questions? All right, I'm pausing for effect because we can do better than this on ARM. Here we've got a 3-instruction solution, but I know we mentioned it, we just haven't seen it until now. The branches aren't the only instructions that are conditional in ARM. Lots of instructions can be conditionally executed. In fact, you can think of the conditional execution of a branch as really the same mechanism that lots and lots of instructions can use. Those are just instructions that take a branch if a condition is true. We can have instructions that are only executed if a condition is true, and we do this with another little suffix on the instruction. So subtract and add and a bunch of other instructions can take the same 2-character code at the end. And just like with a branch, it means only execute this instruction if this condition is met. So instead of having a branch that skips over this instruction if the result is non-negative, we could mark the instruction to say only do this instruction if the result is non-negative. That would be sub, well, that's the subtract, same one we were doing over here. And then the mi suffix says, it's really the opposite of the pl. That was if plus, if positive. The mi is if negative, if the sign bit is set. So this is only going to do the subtract if the result is minus. Well, previously we would have skipped this instruction if the instruction is plus, so we're getting the same thing. This only gets done if the result is negative, the result of this comparison up here. But doing it this way, we don't need this branch at all. We just made this instruction so it only gets executed when we need to negate this value. And that saves us an instruction. And maybe even more importantly, it avoids jumping around the code. And we'll talk in a moment about why that's important. Not all the instructions, but many instructions in ARM can take a suffix like this. And like we just saw, this often lets us reduce the length of code. It lets us save an instruction, maybe save a branch instruction. But the main reason for supporting this is it lets us run the instruction pipeline more efficiently. We talked about this earlier in the lecture, but I didn't really explain it. Executing instructions, this is true of RISC architectures and any modern processor architecture. They don't really just go get an instruction, do what that instruction says, save the results, and then start the next instruction. They overlap the execution of multiple instructions, kind of like you would if you were assembling cars. You would assemble them on some kind of assembly line. And if, I don't know if you need this, but if you got an assembly line of cars, you got one car that's maybe in an early stage of assembly, and the one in front of it maybe is a little more assembled, and the one in front of that is a little further along. So even though it might take a long time for any one car to get from the start of the pipeline to the end, once you've got that pipeline saturated with cars, you can turn out one car after another pretty quickly. The same kind of thing can be done with CPU instructions. If instead of thinking of them as executing just one instruction till it's done and then starting on the next instruction, what if you've got one instruction that's just started executing, and the one before it in the code is a little further along in executing, and the one before that is a little further along? You could have a processor that can complete instructions one after another pretty quickly, even one every clock tick, even if some of those instructions took more than one clock tick to do. That's what RISC processors are designed to do. And like I said, really any modern processor is going to take advantage of this to an extent. We can think of the execution of instruction as having at least 3 stages. A fetch stage where we go get the instruction out of memory. And since memory is slow, even cache might be slow compared to the processor, that's going to take a moment. And then the encoding the instruction is a little tricky to make sense of. So maybe that's the next stage, just figuring out what the instruction is telling the processor to do. And then we actually perform the instruction. We actually modify the contents of registers, or we actually write the result to memory. So executing an instruction requires fetch, decode, and doing an instruction requires those 3 stages. We could have more stages, and that could make things go faster, but this is at least a simple model to think through. So let's say we had a piece of code like the left. It's got a load, an add, a branch, a move, a bunch of other things. So those are the instructions. And let's pretend we're going to start running the code. So maybe we go fetch the load instruction. And then next, we're going to have to decode the load instruction. But while that's happening, we can be fetching the add instruction. And then, so I didn't say this, but we'll pretend the horizontal axis is time. I know that was on the slide, but I didn't say it. And then so once we've decoded the load instruction, we can execute that, and we can start decoding the add instruction and fetching the next instruction. And we can keep on doing this. The problem is when we get to this break, so we can have a bunch of instructions, even if some of them take multiple clock ticks to execute, as long as we can keep this pipeline saturated, then we can finish executing one instruction after another in a single clock tick. The problem happens when a branch occurs. We see that branch if equal there. Should we go get the next move instruction and put it in the pipeline? Should we go get the compare instruction down at the bottom? It really depends on how the branch is going to go. Modern processors have branch prediction built in, where they look at past behavior and try to decide which instruction to work on in the pipeline next. Early ARM just assumed that the branch did not get taken, so it would just go get the next instruction in memory. And then if it was wrong, it might have to, like when that branch instruction actually got executed, that's when we know whether or not we should have gone this way. And if the compare gets done rather than this move, that means we just wasted a little bit of work decoding the move instruction and fetching the store instruction that we never ended up executing anyway. In that case, we would have to reload the pipeline, and it would slow down execution a little bit. If we're lucky and the branch doesn't get taken, then we've got the stuff we need in the pipeline. Again, if we guessed wrong, if we loaded the pipeline with the wrong things, then we've just wasted a little bit of work. We're going to have to flush the pipeline, undo anything from partially executed instructions, and reload the pipeline from the direction the branch actually goes. These conditionally executed instructions are an effort to reduce when that has to happen, to make it so you don't have to flush the pipeline as often, because you don't actually have to take a branch as often. If we can do this, if we can keep the pipeline saturated and we don't have to flush it, then we can get much faster performance. That's what this is trying to show. If every instruction, let's pretend it takes 3 clock ticks, 1 to fetch, 1 to decode, and 1 to execute. If we had no pipelining, then every instruction takes 3 clock ticks. If we used a pipeline with 1 stage to fetch, 1 stage to decode, and 1 stage to execute, then our execution could get almost 3 times as fast. More specifically, if you had to execute n instructions, then it's going to take 2 clock ticks just to saturate the pipeline, but then you're going to start executing instructions. And an instruction is going to finish every clock tick after that, at least as long as you don't have to take a branch, as long as you don't have to flush the pipeline. So if you had a pipeline of depth 3, it effectively increases your execution speed by a factor of 3. You get to a factor of 3 compared to executing an instruction and letting it finish before you start on the next instruction. So if we can avoid branches, if we can avoid having to flush the pipeline, that's going to make our processor a lot faster. And like I said a moment ago, that's what instructions like this are for. If we could solve the same problem with a conditional execution, then as instructions run, we can start loading them into the pipeline. So here we'll pretend we're executing the load instruction, we're decoding the compare instruction, and we're going ahead and fetching this subtract instruction in case it ends up getting executed. We keep running instructions through the pipeline. If this isn't a branch, if it's just a conditionally executed instruction, then when it's time to execute it, we can decide whether to execute it or not based on the condition codes. But if we didn't have to branch, then even if the instruction ends up not doing anything, we've still got the next instructions we're going to need to execute already loaded into the pipeline, so the system can continue to run efficiently. So that was a side trip to talk about pipelining that's built into modern processors, and I think it's especially easy to understand here, and it helps explain why instructions like this make a lot of sense. Questions before we move on? All right, I've got some sad news about immediate data, or maybe said a different way. ARM does some awfully clever things to support immediate data, and we're about to see a little bit of that. You've seen a lot of instructions take immediate operands, like with the add instruction, 2 of the operands are going to be registers, but the 3rd one can be immediate, so you could add an immediate 1, you could add an immediate 10, you could add an immediate 100 if you want. But you can't actually add an immediate 999. If you try to compile this, the assembler will say, I can't do that. I can't add an immediate 999. You could add an immediate 1000. It's not just an issue of magnitude. 1000 works as an immediate value, but not 1001. And I'm about to try to explain why this is and kind of what cleverness is going on with immediate values. And hopefully it'll make a lot of sense. Remember, for immediate values, Intel used, at least 8086, used extra bytes in the instruction. If you needed a byte-sized immediate value, then there was an extra byte in the instructions encoding. And if you needed a word-sized immediate value, there were 2 extra bytes in the instruction. And this made sense because Intel's instructions, 8086, were variable length. But we already know ARM instructions are all the same length. That makes fetching a lot easier because when it's time to go get the next instruction, even if you haven't decoded the previous one yet, you know it's going to be the next 32 bits. So that makes a lot of sense for running the pipeline. But if all instructions are 32 bits, then that's going to limit how much immediate data I can put in the instruction. For instance, if I had an immediate value that was 32 bits, that would use the whole instruction. I wouldn't have any bits left over for anything else. And that instruction has to, I mean, if you back up and look at these examples, those 32 bits have to say what the instruction opcode is. They might have to say one or more operands and some immediate data. So we can't afford to spend all 32 bits on immediate data. In fact, ARM just uses 12 bits for immediate data. And that's what limits the immediate values that can show up in an instruction. And it's not just using a 12-bit number, it's doing what I'm trying to show here. Of those 12 bits, it uses 8 bits to specify a value. So it's got an 8-bit value. If you wanted to think of that as a number, it's a number between 0 and 255. We got 4 bits left over. It uses those as a rotate for that value. So it takes the 8-bit data you give it and it slides it, I'll say it slides it left or right by some number of bits. The reason I'm being vague there is so I can go back and say it right. So that 4-bit rotate value, well, with 4 bits, I can say a number between 0 and 15. The processor takes that rotation, doubles it, and then rotates the 8 bits to the right by that number. So informally, you could say it slides them to the right. Now, sliding them to the right seems like a weird thing to do, because if it was just a shift, all the bits would fall off the low order end if you slid them to the right. But it's a rotate, and remember that means bits that fall off the low order end get put back in on the high order end. So I don't lose any bits by that. I guess if those 8 bits, and let me go ahead and say they start out in the low order 8 bits and then they get rotated where you want. It seems like rotating them to the left would be more useful, but it doesn't really matter. If they fall off to the right, they show up on the left. So that right rotate you can think of as a left rotate if you want, just with 32 minus whatever the offset is. So effectively, we're going to use that to move the bits either way you want. It's just the offset the rotation is expressed as a rotate to the right. So the way this works is you take an 8-bit number where all the bits are in the low order bits, and then you take the rotation, you double that, and notice if I started with a number in the range of 0 to 15 and I double it, now I've got an even number in the range 0 to 30. So I can slide those bits left or right by any offset I want, as long as it's a multiple 2, any even offset. So this lets us specify a lot of different values. Effectively, you get to pick a value for some bits and then slide it into the bits you want to use. But it does limit the bits you can specify. This shows how you can think of the rotation amount if you want. So starting over at the right side of the table, if you say don't rotate at all, rotate by 0, then whatever 8 bits you give are just going to be in the low order 8 bits. But if you say rotate by an offset of F, or in decimal 15, well, that's 15 to the right, so that's the same as a rotate 2 to the left. So that'll take your 8 bits and slide them to the left by 2, effectively multiplying them by 4 if you want to think of it as a number. If you gave E as the rotation amount, it's going to take your 8 bits and slide them to the left by 4 bits, effectively multiplying them by 16. I won't read through the whole table, But if you want, you can slide them to the left by 6 bits or 8 bits or any even number of bits. Questions so far? So if you said rotate 14 bits to the right, that'd be the same as saying rotate, sorry, I said 14, I was reading this E. If you gave E as the rotation, that means rotate 28 bits to the right, twice that many bits to the right, which is the same as saying rotate to the left by 4. So if this was your 8-bit value, this isn't hex or anything. This is just pretend these are any bits you want. And you said rotate those to the right by 28 bits, and that would be by putting an E in the rotation, then your immediate value would look like this. The bits you specified in the value rotated to the left by 4 bits, the same as rotating them to the right by 8 bits. If you said rotate to the right by 24 bits, you would say that with C, and that'd be the same as rotating them to the left by 8 bits. Or any amount you want. If you rotate to the right by 2 bits, your bits will slide to the right by 2 positions, and the 2 that were over here at the right will wrap around to the left. This gives you a lot of power to express different constants. You've only got 12 bits for the immediate value, so you can't specify arbitrary constants. But hopefully a lot of the constants you actually need can be specified like this, like that 1,000 we talked about a moment ago. Well, 1,000 in decimal is, well, I won't read it, but I wrote it out in binary here. So that's what it looks like in binary. Now that is the same as this times 4. I just chopped off the 2 low order bits and put a times 4, since those were zeros anyway. And now I've just got 8 bits that I need. That's 8 bits of non-zero values. So I could specify that as my value. Those are my 8 bits. And then I just need to slide those to the left by 2 bits to get 1,000. And that's what F does. F in the rotation part slides to the left by 2 bits. So I can express that with this as the value. In hex, that's FA, and F as the rotation. But this also shows us why immediate values like 999 don't work. Because if you wrote that out in binary, it looks like this, and there's the 8 bits you get to work with, and then 2 more bits of 1s that you can't have, at least not in an immediate value. Same thing with 1,001. There are the 8 bits you can have. You can rotate them anywhere you want, as long as it's an even amount of rotation. But there's a 1 that you can't have in the value. So these 2 constants don't work. The assembler will tell you if you try to use an immediate value. What if you try to use an immediate value you can't have? Well, that just means you're going to have to get that value some other way. If you let me back up, if you wanted to do this, but you can't use an immediate value like that, you might have to use, typically you would use the LDR instruction to load a value into a register. And the assembler is smart enough to say, oh, if you give me an immediate value to load, and I can't actually store it as an immediate value, it'll store it in a list of constants, and then it'll load from the memory where that constant is stored. So this is summarizing all the instructions that we've talked about, along with 2 of them, well, a few of them that we didn't talk about. All of these instructions, at least many of these instructions, can be conditionally executed. Here's a column for that, and I sort of misspoke. All of the ones in this table can be conditionally executed. So they'll take a suffix like MI or PL, so they'll only get executed if certain condition codes are set. Many of them can optionally set the condition codes, and that's what this column says. So The move instruction can optionally set the condition code. Add and subtract can optionally set the condition code, but not load and store. They never set the condition codes, and you can't put an S at the end to tell them to do that. Some of them, like compare, always set the condition codes. We already said that, so you don't need to put the S there. It wouldn't do anything anyway. That's our quick summary of ARM. I think in this, we've seen a lot of things that are common among RISC processors. We've only got about 5 minutes left, but let's see if we can talk a little bit about how we're going to do some ARM programming and some other details. Yeah.
With immediate values, like memory addresses are stored as immediate values. How are we? What if there's a memory address that
they were in 8086, but in ARM they're not just immediate values. I'm trying to look back at the slide that would show. I mean, it didn't really show it, but here, so here we're getting an address, and ARM has a different instruction for doing that. It doesn't just use an immediate value for that.
But I mean, how would that address be stored in the instruction if it's limited to, like, would that also have restrictions? I feel like that'd be a problem.
I think the restrictions for that are in the form of how many variables can you have access to. So I think there's a table of your variables, and you can load the address of any one of those variables. But there's a limit to how many of those variables or how big the data section of your program can be. But I think it's a pretty big limit. I'd have to go back and look at how those instructions are encoded. And the readings do spend a little bit of time saying this instruction is encoded this way. We just don't have those in the lectures, or we don't have that material in the lecture. But I think for variables, there's a different encoding for that. It's not just it's not the same thing as an immediate value. And the same thing for constants. I think whenever you specify a constant, it's saying, oh, let me go put that in your table of constants. And then when you ask me to get it, I'm just going to load it out of that table.
I guess since the LDR instruction doesn't have as many parameters, maybe it can store more data.
Yeah, and well, it's not necessarily storing an address, because you still have the same problem there. If your address is 32 bits and you put a 32-bit address in your instruction, then there's no room for anything else. So I think it uses a different mechanism for keeping up with variables used in the program and for all the constants used in the program. We saw something a little bit like that with Java bytecode, even though we didn't look at it in that much detail. All right, let me see if I can get through a little bit of how we're actually going to do ARM coding, instruction coding, because I fired up my Raspberry Pi this morning, and I think it uses ARM. I didn't get very far trying to write it, but not everybody's got a Raspberry Pi to play with. And even though your phone may use ARM, you may not have a development environment on that. So we're going to have something that we can use. Fortunately, there's a program called ARMSim that simulates the ARM processor and includes an assembler for assembling ARM programs. It also includes support for a software-generated interrupt, including what look like system calls when we fire that interrupt. So that's kind of like what we've been doing with firing interrupt 21 whenever we needed to make a system call on DOSBox. It only supports file access, so at least for what we're going to do, we just need to read and write files. We won't need to do keyboard input. So we're only going to need a few system calls, and that's what's listed here. They're not, the numbers don't match. They're not the same kind of system calls we used in 8086, but the same idea. Firing different software interrupts, interrupt 66, interrupt 68, 69, and 6A, let you effectively make system calls. And here's what these four do. 66 opens a file You have to tell it what file to try to open. So you pass this a parameter in R0 that's a pointer to the file name you want to open. Sorry, these are highlighted on the next slide. And R1 needs to be a flag that says whether you want to read the file or do you want to write to the file. And if it's successful, it returns a file handle for you. So a small number that is like a file descriptor in Unix that is your way of identifying that file. Once you have a file open, you'll eventually need to close it. You just need to give back the file handle by raising software interrupt 68 and passing in the same file handle. I'm almost out of time, but let me see if I can get through the next two. They're pretty easy. And then there are system calls for writing and reading arrays of data, strings to that file. If you want to write, you set R0 to the file handle you want to write to, and R1 to a pointer to the start of that string in memory, and it will write a null terminated string, the contents of a null terminated string to the file. So notice here, no $ end of string marker, the usual C convention of using a null terminated string. And then if you want to read from a file, you tell it what file you want to read from in R0, a pointer to an array, or really a region in memory where you want that read into. And then for R2, you say what capacity you have, how many bytes you've got room to read from. And then you raise software interrupt 6A, and it'll return with R0 telling you how much. Here it says number written, but I'm sure that's, well, number copied into your buffer, how much you successfully read. This call will read a line of text. So it reads up until either Windows style or Unix style line termination, and it puts a null terminator at the end. So for a line of text, you get a null terminated string. And that's about all we're going to have time for today, but this is what I mentioned before. When we write assembly language programs in ARM, we can declare data kind of like we did in 8086. And we're just about to go through the language for doing that, but we'll save that for next time. Questions before we call it a day? All right, I'll hang around if people have questions after class. Let me go ahead and stop recording.